The Chinese lunar probe has successfully taken off from the far side of the moon to start its journey back to Earth. The Chang'e 6 module landed on Saturday in a volcanic basin close to the moon's south pole and has collected samples of rock and soil.
The moon isn't what you think it is. What China actually discovered on the moon is unlike anything you've ever heard. When China's Chang'e 6 capsule returned to Earth with samples from the moon's far side, the first dust it carried didn't match anything collected by the Apollo missions. The grains clumped strangely, looked unlike any lunar soil we'd seen before.
China's lunar probe has landed, carrying samples from an unexplored far side of the moon. The Chang'e 6 mission, which lasted for 53 days, explored the side of the moon that faces away from the Earth. It blasted off from the Wenchang Satellite Launch Center
and pointed to a colder, drier interior hidden beneath the far side. In this video, we break down what China found, grain by grain, and show how just a few grams of soil reveal a two-faced moon, born from a violent collision with Earth. By the end, the moon you thought you knew will feel like a completely different world when the far side dust misbehaved. The first real surprise from Chang'e 6 started with dust on a tray. Inside a lab in China, technicians opened the container from the far side of the moon and poured out a small amount of soil. They expected what everyone already knew from Apollo footage and earlier Chinese missions: fine gray powder that behaves almost like a liquid when you tilt it. But that is not what they saw. When they gently moved the tray, the grains from the Chang'e 6 site did not flow smoothly. They tended to move in small clumps, break apart, then stick together again. The people handling it described it as thicker, stickier, and lumpier than the near-side moon samples they were used to. Under the microscope, the difference became clearer. Classic near-side mare soil often looks dark and fairly uniform, full of tiny glass and basalt fragments. The far-side soil from Chang'e 6 appeared slightly lighter overall. It had more bright mineral chips mixed in, pieces that matched the old highland crust rather than just dark lava rock. There were still glassy impact fragments there, but the mix felt more chaotic, as if several different kinds of terrain had been ground together. All of this came from less than 2 kilograms of material, a few scoopfuls of dust and rock, collected by a robotic arm in a crater we never see from Earth. We're already telling a completely different story about the moon than the one written from Apollo and Chang'e 5 samples alone. In the lab, the tone was careful. People asked simple, direct questions. Why does this soil clump more? Why is there so much highland material mixed into a basin that was supposed to be covered in basalt? Why do the temperature estimates for the ancient lava come out lower on the far side? No one could answer those questions yet. What they did know was that the first grains from the hidden hemisphere were not just a repeat of what had already been brought back from the near side. From the very first tests, the far side samples behaved like evidence from a slightly different moon, which meant that something deeper in the story had to be rechecked. How China reached the side we never see. To understand why this new dust matters, you first have to understand how hard it was to collect it. For most of space history, the far side of the moon has basically been off limits. Not because we could not reach it, but because we could not talk to anything sitting there. The moon blocks radio signals, so a lander on the far side is entirely cut off from Earth. During Apollo, that was a deal breaker. You cannot land astronauts somewhere you lose contact with the moment they touch down. China solved this problem in stages. First came the orbital scouts. Chang'e 1 and Chang'e 2 mapped the surface from above, building detailed 3D models of the craters, slopes, and boulders. These were not just pretty pictures. Engineers used that data to find safe landing ellipses, places where a lander was not likely to hit a hidden rock or slide into a crater. At the same time, scientists were looking for something specific, regions that bordered the huge South Pole Aitken Basin, one of the largest and deepest impact craters in the solar system. Then they put a mirror in place. Before attempting a far-side landing, China launched the Queqiao relay satellite to a gravitational sweet spot behind the moon. From that position, Queqiao can see both Earth and the far side at the same time, catching signals from a lander and bouncing them home. It was like parking a cell tower over the lunar horizon. With the relay working, they sent Chang'e 4. In 2019, Chang'e 4 became the first mission to land softly on the far side, touching down in Von Karman crater, near the center of the South Pole, Aitken Basin. Its rover, Yutu-2, began driving across the surface, taking close-up images of rocks, measuring their spectra, and using radar to detect layers beneath the surface. That mission proved two important things. First, China could guide and operate a robot where no one else had gone. Second, the far side of the moon was noticeably different in detail compared to the near side, even before any samples came back. Chang'e 5 was the next step, but it went to the near side. In 2020, it landed in Oceanus Procellarum, drilled and scooped up about 1.7 kilograms of soil and rock, then launched that material back to Earth. This was a full end-to-end test of sample return, precision landing, automated drilling, liftoff from the moon, rendezvous in orbit, and a re-entry capsule surviving the plunge through our atmosphere. It worked on the first try. Only after all that did Chang'e 6 get the green light to do the hard version, repeat the sample return, but this time from the far side. For Chang'e 6, engineers had to combine every part of their earlier experience. They used far-side terrain data from the orbiters, communications via Queqiao, landing and surface operations experience from Chang'e 4, and the sample return architecture from Chang'e 5. The target was a basin within South Pole Aitken, a region where ancient impacts may have dug so deep that material from the moon's interior was thrown closer to the surface. From the outside, the mission looked calm. A Long March rocket launched from China's coast, sent the spacecraft into lunar orbit. Then the lander separated and dropped gently toward the far side under automatic control. There was no live video in most countries, no astronaut audio. Just a steady stream of status updates as the lander touched down, drilled, scooped, and sealed less than 2 kilograms of soil into a small return capsule. The hard part was invisible. Every command went from Earth to Queqiao, then down to the surface. Every status message and every image followed the same path back. Timing had to be precise. There was no option for a human pilot to correct a last-second problem. By the time the Chang'e 6 return capsule streaked back through Earth's atmosphere and hit the ground in Inner Mongolia, the risk was mostly over. The capsule itself looked simple, a small burnt shell sitting in the grass. Inside, though, were the first physical samples ever taken from the side of the moon we never see. That is the material that ended up on the tray in the lab, and that is why people are paying so much attention to the way those grains behave. While Chang'e 6 brought the first far-side soil back to Earth, China had already been sending scouts across that mysterious terrain, uncovering clues that set the stage for what the samples would reveal. The bunny rock and the mantle shrapnel. Before Chang'e 6 ever dug into the far side, China already had a scout on the ground. That scout was Yutu-2, the small rover that rolled off the Chang'e 4 lander in early 2019 and began driving across the von Karman crater, deep inside the South Pole Aitken Basin. Most people outside the scientific team first heard about Yutu-2 because of a blurry picture. One day, the rover's navigation camera caught a blocky silhouette on the horizon. It looked almost like a little hut sitting on the edge of a crater. Chinese outreach channels called it a mysterious hut, while Western headlines turned it into a moon cube, and the image spread quickly online. From the rover team's point of view, it was simple. The object was about 80 meters away, the lighting was harsh, and the camera was not meant for pretty landscape shots. Anything bright at that distance was going to look square and sharply edged. Still, it was a good target. They plotted a slow route over the next lunar days and drove Yutu-2 toward it. The closer the rover came, the less it looked like a cube. Higher resolution images showed an irregular boulder sitting on the rim of a small crater with a tiny rock in front of it. From one angle, the boulder did not look like a hut at all. It looked like a crouching rabbit with a carrot at its feet. The team started calling it the Jade Rabbit Rock. That small episode was useful in two ways. It reminded everyone how easy it is to read structure into low-quality images, and it also gave a sense of the terrain that Yutu-2 was navigating. The far side surface is scattered with boulders, impact fragments, and mixed material. It is not a smooth lava plain. While the Mystery Cube story faded from the news, the more important work continued quietly. Yutu-2 carried instruments that were designed to read the moon, not just photograph it. One of the key tools was the visible and near-infrared spectrometer. It shines light on rocks and soil, then measures which wavelengths are absorbed. Those absorption patterns tell you what minerals are present. In the Von Karman crater, the spectrometer kept detecting mineral combinations that did not match the simple surface crust. The spectra showed strong signatures of low-calcium pyroxene and olivine, minerals common in the deeper layers of planetary interiors. By comparing those patterns with models, scientists concluded that some of the material around the rover was likely mantle-related, meaning it was not born in the shallow crust alone. It had probably been excavated and thrown outward by very large impacts that reached down into the moon. The location helps explain this find. South Pole Aitken is one of the largest impact basins in the solar system, more than 2,000 kilometers across and 13 kilometers deep. When something that large hits, it does not just scoop out a little crater, it digs into the lower crust and possibly the upper mantle. Over time, later impacts churn and mix. That ejecta U-22 was essentially driving on ground that had been stirred by one of the most violent events in lunar history. The rover also carried ground-penetrating radar. As it rolled along, it sent radio pulses into the surface and recorded echoes from buried layers. The radar profiles showed a thick blanket of regolith on top, then stacked zones of broken rock, buried blocks, and older lava flows. Instead of a single layer of dust over solid rock, the subsurface was a layered record of impacts and eruptions, tens of meters deep. Taken together, the spectrometer and radar data were an early hint that the far side is more than just a different-looking surface. The rocks around U-22 appeared to include fragments of deeper material, and the radar cross-section suggested a long, complex history of resurfacing. As U-22 mapped the moon's far side, Chang'e 5 was already preparing to show that the near side, too, was full of secrets waiting to be discovered. The moon was never as simple as we thought. By the time Chang'e 6 was on its way to the far side, China had already learned something important from the near side. The old idea of a dry, uniform moon was not holding up very well, and that change started with Chang'e 5. In late 2020, Chang'e 5 landed in Oceanus Procellarum, collected about 1.7 kilograms of soil and rock, and sent it back to Earth. On the surface, it looked familiar, a gray powder from a dark lava plain, not very different from the Apollo sites. The surprise came when scientists began looking at it grain by grain. One of the first headlines was about a new mineral. In thin sections and under electron microscopes, researchers found tiny colorless crystals with a structure no one had seen in natural rocks before. They named it Chang'e Y, after the Chang'e missions. Chemically, it belongs to the phosphate family, but as a distinct species, it was unknown from Earth. It was microscopic, but it sent a clear message. Even in regions we thought we understood, the moon still had ways to surprise geologists. The same samples were fed into another favorite topic, helium-3. For years, people have discussed helium-3 in lunar soil as a future fuel for advanced nuclear fusion. Chang'e 5 gave researchers fresh material to measure. They confirmed that the regolith does contain helium-3 implanted by the solar wind. Along with other light gases, that part matched earlier estimates. What the data also showed, however, is how thinly that resource is spread. The concentration per kilogram of soil is tiny. Any realistic mining scheme would need to move and process huge volumes of regolith to get useful amounts. It is a useful detail for engineers, and it makes good copy in energy discussions, but in the lab, the focus was less on science fiction power plants and more on what these gases say about the way the lunar surface has been exposed to space for billions of years. Then there was the water story, which became even more complicated. For a long time, the safe line was that the moon is basically dry. Later work with Apollo samples and orbital data disproved this. There are polar cold traps with ice, and hydrogen and hydroxyl are bound within minerals, and glass Chang'e 5 added a new piece. In some grains, scientists found a mineral they provisionally called ULM1, Unknown Lunar Mineral 1. It turned out to be a hydrated salt, a magnesium chloride crystal that contains intact water molecules and ammonium inside its structure. In other words, this was not just a dry crystal with a bit of hydrogen in its lattice. It was more like a tiny cage holding water and ammonia, together with magnesium and chlorine. The key detail is where it was found. ULM1 came from sunlit mid-latitude soil, not from a dark polar crater. Models and lab tests suggest it can stay stable in a vacuum at the temperatures that regular surface grains experience there. That means that real molecular water can survive in mineral form in places where simple ice would quickly disappear. Put together, these findings push the picture of the moon away from a simple dry rock and towards something more layered. There is a new mineral that does not match anything in Earth's rocks. So far, solar wind gases and helium-3 are recorded in the soil. There is water and ammonia locked in tiny salt crystals in ordinary sunlit regolith. Because of these findings, by the time Chang'e 6 touched down on the far side, researchers already knew that near-side basalts could hide unexpected minerals and hydrated salts. The question was whether the hidden hemisphere would follow the same pattern or reveal a different kind of history entirely. The answer to that would come from the numbers in the lab once the far side dust joined the near side samples on the same tables. 2 faces of one moon. When the first detailed reports from the Chang'e 6 samples came out, the focus moved from how the dust looked in the lab to what its chemistry was saying about the inside of the moon. That was the moment the far side stopped, being just a new location on the map, and started to look like a completely different thermal engine. Geochemists started with the basics. They dated the tiny crystals in the Chang'e 6 basalts and confirmed the age of the lava that created them, about 2.8 billion years. That puts these rocks in the same broad time frame as some of the younger volcanic activity on the near side. In other words, both hemispheres were still erupting around that period. The question was whether they were doing it under the same conditions. To answer that, the teams used the mineral data as a thermometer. The composition of pyroxene, plagioclase, and other phases in the grains can be used to plug into petrological models to estimate the temperature at which the magma cooled and crystallized. For near-side sites like Apollo landing zones and the Chang'e 5 area, those models indicate crystallization temperatures around 2,200 degrees Fahrenheit. For the far side, Chang'e 6 lavas, the answer kept coming out lower, around 2,000 degrees. A difference of 200 degrees does not sound dramatic in everyday terms, but in deep interior geology, it is a clear signal. Melting the mantle and keeping magma moving for billions of years demands heat. If one side of the moon were consistently erupting from cooler material, that side would have access to fewer heat-producing elements all along. Water content pointed in the same direction. By measuring water in apatite and melt inclusions inside the Chang'e 6 grains, and then working back to the original magma, researchers estimated the mantle source under the far side site contains only about 1 to 1.5 micrograms of water per gram of rock. That is at the bottom edge of what has been inferred for the near side mantle, where some regions reach up to 200 micrograms per gram. Taken together, the message was simple. The mantle feeding the far side basin that Chang'e 6 sampled is colder and drier than the mantle beneath the near side. It is not a small local difference. It is a pattern that matches the long-standing observational split between a smoother, darker near side and a thicker, more cratered far side. The far side samples added something else, a clean test of a bigger idea. Modern versions of the giant impact theory, known as the Big Splash, do not just say that a collision formed the moon from debris. They also predict that after that event, heat-producing elements and some volatiles would have become unevenly distributed, leaving one hemisphere enriched and hotter and the other poorer and cooler. Remote sensing had already suggested that the near side is richer in thorium and other heat-producing elements. The Chang'e 6 numbers gave this theory physical backing from real rocks. What China found in those far side samples is not a single object or a hidden structure. It is sample-based evidence that the moon is internally two-faced, with a hotter, more volatile and friendlier near side mantle and a cooler, almost desert-dry far side mantle. Exactly the kind of split you would expect from a body born in the chaotic aftermath of a giant impact with the early Earth. That is why the texture of the dust, the lighter mix of highland fragments, the cooler crystallization temperatures, and the low water content matter so much. They are all different views of the same underlying fact. The side of the moon we never see is not just another patch of gray ground. It is the surface expression of an entirely different interior story, one that any future model of the moon's origin now has to match, grain by grain, after the dust settled. Once the first wave of Chang'e 6 results came out, the tone inside the lunar science community shifted from surprise to adjustment. No one threw out their models overnight. Instead, people started asking what it means to work with a moon that is clearly split inside, not just on the surface. On the scientific side, the far side samples became a new reference point. Any theory about how the moon formed and cooled now has to do two things at once. It has to explain why the near side carries more heat-producing elements and water in its mantle, and why the far side under South Pole Aitken is colder, drier, and supports a different style of volcanism. A simple, uniform picture of a magma ocean is no longer enough. Models are moving toward messier scenarios, with uneven cooling, pockets of enriched material, and long-term differences in how each hemisphere retains its heat. There are practical consequences, too. For engineers planning future landings, the behavior of the soil matters. The thicker, stickier, lumpier regolith that Chang'e 6 brought back suggests that far-side dust may respond differently under wheels, drills, and construction equipment than the loose powder seen at Apollo sites. It might be better for compacting into bricks, but it might also demand different designs for rover traction and dust mitigation. These are not abstract questions if you plan to put hardware, or eventually people, in that environment. The volatile story is also less theoretical now. With Chang'e Y, ULM 1-hydrated salts, trace water and minerals, and helium-3 in the soil, there is a growing list of ways the moon has stored and moved small amounts of gas and water. None of these on their own turns the moon into an easy refueling station, but together they outline a real, if thin, lunar water cycle. Ancient volcanism, solar wind, polar cold traps, and sunlit hydrated minerals now sit in the same picture. For China, these results are also a statement of their lunar knowledge and experience. In a little over a decade, the program went from orbiters to landers, then to rovers, then to sample returns from both the near side and the far side. Each mission added a layer of detail, and together they produced a result that changes how everyone needs to think about the moon. From here, the next steps are deeper. More far-side landings, drilling into thicker sections of the South Pole Aitken Basin, and eventually bringing back larger cores instead of just scooped soil. With every new sample, the internal map of the moon's two faces will get sharper. The mystery now is not whether the moon is split, but how that split started, and how much of that early chaos is still written in the dust waiting to be collected. If the first handful of dust from the far side already forced us to redraw the moon from the inside out, what do you think we are going to find when we start drilling deeper into that hidden hemisphere? Let us know in the comments. Thank you for watching this video with us. We'll catch you in the next one.